Hello, and welcome to another exciting episode of Cooking with Unity, episode 43. I'm your host, Maximilian Moreau, and with me is my tech, Philip Wilson.
Yep, it's episode 43.
It is episode 43, and today we're going to start a pinball game. So, the reason we're doing this is because we've done some physics stuff in the past, some basic collision stuff. This is going to be the first time that we did a little bit on the physics platform, but we didn't solve a lot of our problems with that. We just kind of made it work and had some physics. This is going to be one where it's really reliant on the collision working properly and consistently, and it's going to take some trial and error to get things set up exactly right. I want to do this episode because collision can be a tricky beast. We've had troubles with it even in simple cases, and we're going to be doing some more complex stuff like basically having flippers that actually flip things. We're going to have things that apply forces in various places, and we're going to want to make sure that we can get everything working so that it looks somewhat like you'd expect for a pinball machine or some pinball-like game, but also still maintain control of the ball and still maintain control of the situation. So what we're going to start with is, I guess we're going to need a play area. So let's make let's start with a plane.
Cool.
And we're going to put it 0, 0, 0, and I'm going to go ahead and make the camera be at 0, 0, -10. And so this is going to be our main play area. I'm going to also just really quickly throw in just our token directional lights so that things have some lighting to them. So this is going to be our back face. This is going to be where the ball is actually rolling on top of. So what's nice is in Unity, we're probably already set up for that. If we were to create a sphere here and put it on top of the surface here, and then we just add a component, physics, rigid body, we should have a case where it will fall and stay still on the plane. So actually maybe we do want the camera up a little.
Yeah, maybe.
Yeah, let's put it back to the 1, whatever. So we have the plane here, and if we rotate our plane, we're going to basically rotate it so that it's not completely flat, so that the ball will roll around. So if we rotate this along the x-axis, you should see. Oh yeah, so nothing has happened. So the reason it hasn't just worked is because this sphere, the rotation that I've just applied, has not gone through the physics system. It hasn't asked the physics system it's okay for this. So the sphere thinks that nothing has changed. If we were to actually take the sphere and move it, that will probably fix that. So if we just take the sphere, take its Y position and put it up in the air just a little bit, it'll start hitting and rolling as we would expect, and there it rolls off. So the way we're going to do this is we're just going to angle things and have that. Actually, that's not what we're going to do. We're going to let's actually, before I say we're going to do that, I want to see what the gravity system looks like in the editor. So if we go to physics, yeah, we're just going to rotate the plane. We could actually affect the direction, the vector of gravity, but this is kind of needless to work with. I don't think it'll hurt us too much to.
But you could theoretically start changing gravity around if you wanted to.
Yeah.
Should actually be kind of cool in certain situations. Maybe not right now, though.
Yeah, we may switch back to that as the strategy, depending on how we do with this. Let's just see where we get from here first. So we have a basic play area. Yeah, really basic play area right now. Let's pick an angle. Let's just put it at I don't know. Let's do 20 degrees. Sorry, -20 degrees, I guess.
Oh, that looks good.
And hit play and just see how fast a ball we get on that. So that's going to be a little slow, but it's probably better for us to work with at first, to just be slow about things and kind of get a feel for what we're going to be doing. The faster things move in a physical simulation, the more likely you are to run into collision problems, like skipping a collision altogether. And we're going to try and go over how to solve these problems as we go through. So we have a basic thing here. I'm going to make the plane a little bit bigger. We're going to make the Y, actually, sorry, the Z. The Y is not going to do anything. Make it a little bit bigger. Hit play. So there we go. I'm going to move the camera.
Every time I see a marble just fall off screen, all I can think of is the Marble Madness sound.
So we're going to start with kind of a front view of the thing. We'll probably change this later because most of the time you want kind of an overhead view on a pinball machine. This probably is too much perspective. Oh well, at least it gives a concept of what we're doing here.
I think that'll work for right now.
So let's start with that. Let's do a flipper first. I think that's going to be the most basic player interaction component. So let's set something up like that.
Okay.
So I'm going to use a capsule just because it's the most flipper-looking thing that we have to work with built into Unity.
I think that's a good idea.
And we're going to see. Here's what the tricky part is: just getting it all organized so that it.
Yeah, I could see why you were thinking about modifying the gravity.
Yeah.
Due to the fact that it would be so much easier to mess with rotations. Maybe we should modify the gravity a little bit. I bet we could do that. Let's do it.
Yeah, let's do it that way. Let's put this back to
modify that
0.
gravity. Yeah.
So we'll move our camera around a little bit. We'll rotate it kind of downward.
Yeah, we shouldn't be scared to modify things like that. You can always change it back.
Negative 15 here. No, negative 15. Something like that. And project settings, physics. We're just going to apply
negative 981.
Yeah, this is basically Earth gravity here in meters per second. So assuming that your units are meters, that's actually Earth-style gravity, which is why they picked that as your default. I'm going to put a little bit of a negative z in here. Do I want negative or positive? Yeah, I want negative z. So
yeah, definitely negative.
Let's do -3 in the z and see what we get. So if we hit play,
there it goes.
There it goes. And so now it looks like we have an angle on things, even though this is actually totally flat.
That's pretty cool.
And yeah, we'll just work with that for now. Technically, we could lower the downward force as well, but that's not going to be necessary. So now that we have something kind of a configuration we can work with, so our capsule, we're going to want to flip from kind of the end of the capsule. So we're going to need a parent game object for this thing to work properly. So I'm going to create an empty game object. We're going to call this flipper geometry. And then we're going to call the empty game object flipper. And so first let's put everything at like numbers that we can work with. So I'm just going to do 0, 0, 0 and 0, 0, 0. And we're going to so the main thing is we want to make sure that the pivot point is basically right there on that transition between being a
the
cylinder to being a sphere at the end there. So let's just move the flipper geometry down just a little bit in the Y, probably 0.25. Okay, sorry, down negative 0.25. Throw this into the flipper. So now when we rotate, let's actually try 0.5 actually. Yeah, that looks about right. So yeah, that is exactly what we want. So now if we rotate the flipper here along one of these axes.
There it goes.
So that works about right.
So this way it's not rotating from the center point, it's rotating from a side point.
Yes. And orientation. Let's make it so I don't think the orientation will matter terribly much, so I'm not going to put much into that. Let's just get this flipper rotated so that it is
So it's kind of facing a normal direction that we
Yeah.
all recognize. As long as we've all seen pinball machines.
Yeah. So, yeah.
I'm going to rotate it around the Z, right?
I have to rotate it around 2 axes. Oh, there we go.
It's just down a little low.
This actually is not going to work the way I want it to work right now.
Really?
Yeah, I'm messing things up here. Alright,
Oh, I see.
let's rotate the flipper itself.
Good call.
One of these directions.
Should be Z. All right.
So now if we rotate along the y-axis, that rotates. Oh, wait, we're on the geometry again. How did that happen? How does that keep happening?
I do not know, but it needs to stop.
I think it's because I keep clicking on it multiple times and it goes through. So let's try this again.
There we go.
Negative 90.
That is more what
There
you
we
were
go.
expecting.
Yeah, exactly. And I'm going to go ahead and make this a little bit further up. We may actually change this to a box collider too, depending on how we feel in a second here. But
Yeah.
yeah, so let's make sure that these are right on top of this plane. As such, let's make the y 0.5. So that should be right on top of the plane if the plane is
that
0,
1?
which it is.
Yeah, 0, not 1.
So so now if we rotate in the, oops, that's the geometry again.
Be the Y?
Yep, in the y. There we go. We've got a basic flipper action there. So let's start it at like a negative 25 degrees. Does that seem about right?
Yep, that's what I was thinking.
And I'm going to go ahead and switch this back to global coordinates, just to position it on here. Let's just see if it works to deflect the ball without doing anything. Camera is not far enough back, evidently. So,
So, here it comes. Bloop.
alright, it deflected the ball.
How about that?
In a kind of realistic sort of fashion. Let's go ahead and make the flippers a little bit longer. We're just going to scale the
Geometry?
Y.
Ooh.
Oh.
You could scale it on the parent object and it would scale properly.
Yeah, that maintains the pivot point at the very least.
Mhm.
So yeah, let's go with that. Let's do 2. It's kind of a long flipper. Actually, let's do 1.5. No, not 0.15. Rather,
Oh, rather short little flipper there.
yes,
Huh?
rather short little flipper. So this looks like 2.75 to me. So let's duplicate this. Actually, let's create a prefab of this, and then let's duplicate it. And we're going to basically flip this over to the other side. So this will be at negative 2.75.
And what is it?
Actually, let's do the z at 12.5 on both cases. And then this one, we just changed the negative 25 to just 25. Nope.
Oh, what's the right way of doing this?
Whatever, we'll just flip it all the way around.
That's a good call. Oh yeah, you just had to add 180.
Yep.
Oh yeah, math.
Oh yeah, math. Alright, so we have our basic flippers here. We have the ball in a horrible position for actually playing a pinball game, so I'm going to move it over to the right a little bit.
Just goes right down the center.
Let's see if it'll drain. It should. That should be a wide enough space for the ball to drain. Yep. There it goes. Yep. Drains down. So we're going to want to have this flipper actually move. I'm debating on whether we should do this as an animation or just as a physics-y thing.
Well, I'd do it as a script myself.
You do it as a script yourself, yeah. That's because you haven't had a lot of practice with the animation system.
This is also true.
Let's start with the script. We can get fancier with animation stuff later, and this allows more flexibility probably. So,
I just like working with numbers better than with animations.
Yeah. So we're going to call this flipper. So variables that we're going to need. Probably we're going to want a public float, angle, probably max angle. We'll assume the minimum angle is whatever the angle is when it starts.
Mm-hmm. We need a time variable, probably.
Public float. So the amount of time it takes to get from one place to the other.
Correct. It'll be a small number, of course, but
would it be better to do that with time or with kind of a force thing?
I don't know.
Let's do it as time, like you said first. We can always change it. Flip time.
That is the beauty of programming.
And yeah, I don't like that because it doesn't imply the force involved with the operation. Though I'm not sure if we're going to be able to. Well, whatever. Flip time. We can change it later.
Exactly.
Max angle, let's call it 20.0 f. We're going to assume this degree is for right now. And then flip time, we'll say 1.0 f, even though it's a really, really long time for a flip. It's just something to get in there as default.
Yeah, you can always tweak it later. Huh?
And then let's do public float, public string button name.
Oh yeah, forgot about that part.
We'll default it to Fire1 because that's a built-in one on your initial project. When you create a new one, Fire1's already defined and Fire2 is already defined, so we can work with those.
Pretty handy.
So here we go. So all this is gonna do is in the update loop, if input.get button down actually let's do input.get button, and the name will be button name. Rotate the flipper. So there's a whole bunch of ways, I don't know what I clicked there. There's a whole bunch of ways we've learned to rotate things, and in the case of what we're doing now, we probably are going to want to assume that we have a rigid body attached to this thing. Or do we? Let's just try it without first. Let's just see what happens if we just start rotating things through. I think this is not going to work. Yeah, but let's do it the wrong way first, and then we can change it. So transform dot... actually, so we need the initial rotation. As I said, we were just going to imply that whatever it's set to initially is what it is when you're not pressing the button.
Mm-hmm.
So our initial rotation will be transform dot rotation... So we'll need a private variable, private vector 3. Actually, let's do quaternion. Private quaternion initial orientation. So initial orientation equals transform.rotation.
So So I'll just store the
They'll store the initial one. And then, what were we rotating on here? I think it's the y-axis, right? Yeah. All right. So transform dot rotate. Let's do rotate around. So if we do rotate around, so the axis is going to be vector 3. Hold on. Yeah, vector 3 dot up. And the angle will be
is that the max angle?
Yeah, it will be max angle times time dot delta time times so flip times 1.0. So it'll be max angle divided by flip time times time dot delta time.
There we are.
So let's see what this does. Oh, sorry, that's not right. Okay, this is a good starting point to test at least. So we're going to attach this to our flipper. I'm going to do it to the prefab, so it goes to both of these guys, even though obviously one's going to want to be on a different button later. So we hit the button, and there it goes. Whee! And it kind of sort of works.
Oh, that makes me happy.
So I don't think my math is right there, because that looks like it's taking less than a second to go 20 degrees. That may be because we're not. That may be because we're not actually in degrees. This may be in radians. Let's actually check that. Google. We're gonna do transform dot rotate around unity. By degrees, it says by degrees. So obviously our math is wrong then. So max angle divided by flip time. That's probably not right. So seems like that would be right though. We're dividing by 1. That shouldn't be doing anything anyway.
Maybe it's an order of operations problem.
Yeah.
Give it some.
But the thing is, this should be
parens.
like this should be equivalent to this right now. So I don't think that's
Should be.
Well, it is, but not should be. It is.
So it is. Yeah.
Vector 3 up max angle times time dot delta time. I wonder why that's going so fast, because that does seem
rather quick.
So let's just assume that they actually mean radians. Maybe there is a problem here. Let's multiply this by mathf dot deg to rad and see what this changes. That looks about 20 degrees per second.
Yeah.
So I think that they were wrong about what they said in their documentation. This happens sometimes.
Possible.
So I guess they want radians for rotate around, even though it says by angle degrees here. Here, let's just actually triple check this. So let's look at. Oh, I guess clicking does it too. So 206. We're gonna see if it goes about 20 in a second. So okay, so 220. We want it to be 230. 1001. Yeah, that's almost certainly right. So let's go ahead and put our divider again in here. So divided by flip time. So now if we adjust the flip time on here, this should actually do something. So if I make the flip time to be 0.1, we should see one of them moving a lot faster. Yeah. We do see them moving a lot faster.
One of them.
Yeah, because we only changed one of them. So.
Oh yeah, good point.
So I'm going to revert this to the prefab. So that rotates it, but it doesn't stop rotating when it gets to the maximum amount of degrees. So we're going to now check to see the rotation. So if transform dot rotation, let's go with transform dot rotation dot Euler Angles dot y. So minus initial orientation dot Euler Angles dot y. So that's our original rotation. So if this thing is less or is greater than max angle, let's say greater than or equal to equals. If it's greater than or equal to that, then we set the transform dot rotation dot I don't think I can directly set this. Dot y equals max angle.
I don't think you can directly set that either. It'd be so nice if you could. I think you have to throw it into
And
a
actually,
vector
this
three.
be initial orientation plus max angle. Yeah, I think this will give us a complaint, but let's just try it real quick for fun. Cannot modify a return type of engine quaternion Euler angles. Consider storing the value in a temporary variable. So that's what I figured it was going to be. So we need to do quaternion new orientation equals this. Actually, it equals transform dot rotation. And then we set the new orientation dot Euler Angles dot y, or Euler Angles, equals initial orientation plus max angle, and then finally we set transform dot rotation equals new orientation.
All right.
So if we hit play on this,
Got an error.
Still got an error. Oh. This is a different type of problem.
What is it? You can't modify a Euler angle?
Okay, that's interesting. So we can't solve it using our old usual technique.
Really? Let's see.
Alright, well, let's do u vector 3. So it would be x, and finally new orientation dot z. Let's see if this will work. All right, stop complaining. All right, so we hit space or we hit control. There we go. Rotated there, and will not rotate ever again. So good. That's actually kind of what we wanted to do. So now finally we need to do an else statement here and return it back to where we wanted it. Maybe we should have done rotate towards. Well, hindsight 2020 or so, or whatever they say. So let's just copy this.
Okay.
And this time we're going to just put a negative here. And then finally we're going to do minus max angle less than or equal to negative max angle. Or no, that's not what we want. 0 actually. So if the current rotation minus the initial rotation is less than or equal to 0, then we make sure that it gets set to the initial rotation. So,
all right.
And this one actually, we don't even have to do anything fancy here. We can just do new orientation equals, actually we can just do transform dot rotation equals initial rotation, initial orientation.
No, we don't even need those
two lines. We don't need any of
lines.
these things.
That makes it easier.
So let's see if this works now. So we hit our button, it rotates out, we release, it rotates back.
Ah, that's awesome.
All right, so let's set these up so that they actually work a little bit better now. So the one that's working right is the right hand one. This one does what we want it to do. So the left hand one, at the very least, we want to make sure to put the flip time, the max angle to the negative 20. So this will make them both flip out the same way. Ooh, what happened there?
Oh, its definition of 0 is different than the other ones.
What do you mean?
Oh, I mean 0 is the same, but its rotation is different. Its initial rotation. Because, I mean, we can't judge it by 0, I don't believe, can we?
Well, we're subtracting, so we should be able to judge it against 0.
No, that's not the problem. Just me being silly.
Let's try that.
You change this.
Huh. So it works fine in that case.
That is interesting.
But not in the negative case.
Well, if it just keeps going, does it stop at the same location as the other one? Does it look just like it when it stops rotating?
That's a good question. Let's find out.
Look at it go. Look at it go. Nope. Huh. Very interesting.
I'm doing something wrong. Making some assumption here somewhere.
Yeah. Well, it's not the vector up part, is it? No, that should be fine.
Okay, let's So I'm going to guess that this is a problem with using negatives. So if I set this to a positive value like 20, it works kind of how you'd expect, I think.
Except for it's going to rotate the other way when you press the button now, right?
Yeah, no, it's still going to rotate the wrong way. So you go to -1, yep, it starts creeping. And if we slide this up, it's still creeping all the way to positive, and then it creeps and stops.
Interesting.
It's because we're making an assumption about the nature of subtracting these two values. Alright, well, I'm just going to make a special case for negative for right now, and negative and positive. If max angle is greater than 0, we do this, else
mean, wouldn't that take in the negative as well, the bottom part? I mean, isn't that affected by it?
Yeah, I think it is.
We just have to do a big special case, essentially.
I have to be doing this stupidly. All right, let's reorganize this. Let's do something different. Let's just rotate towards instead.
Okay.
I'm going to keep what we have right now just because we have something that's kind of sort of working. And we could just reorient the other flipper and make it so it's positive only. Let's do that. Let's not even worry about it for right now. Let's just do, let's just say that must be positive. And then let's take this thing and rotate it in some non... I don't like math. So 450. 450 looks good for some reason.
Yeah.
So now if we hit play and... Oh, well, this is still at negative, but we want this to be at 0, or no, 20. And let's actually get it rotated into the initial position we want, which is here at some angle close to that. I guess 390 is probably it.
Really?
No, that's not right.
It's probably 380.
Yep, you're right. I think. Are these both in the same? 12.5, 2.75.
What?
Yeah, it's not quite right. 85.
Oh, interesting.
There we go. It's because this one's at a 5 too, isn't it? 35, yeah. So.
Oh, okay.
That makes sense. Oh, that didn't solve a problem. Naturally. Did I rotate the wrong thing? No.
I don't believe you did.
This thing reevaluated itself. I think we ran into something dumb.
Yeah, it definitely reevaluated itself. So what is rotate towards? I don't think I've used that yet.
Alright, let's use rotate towards. Let's give it a shot at least. Rotate towards... let's see what it is before I say what it is. Transform dot rotate. Rotation dot rotate. All right. Need to find it. Unity rotate towards. Where is it actually hidden? Oh, it's in the vector 3 section for some reason.
Vector 3 apparently.
So it's not in definition for rotation, but it's in the definition for vector 3. Rotates the vector towards current towards target. So it returns a vector 3. Is there a quaternion equivalent? Is there a rotate towards quaternion?
That's a good question.
There is. There's a quaternion dot rotate towards. Perfect.
I think that's a little bit better to use, isn't it?
Yeah.
It's essentially the same as quaternion slurp, apparently.
Yep. Spherical lerp.
Linear interpolation.
Yep. All right. So, flipped orientation equals transform okay. Dot. Initial orientation dot rotate. No.
So we want basically an orientation that'll, when it's
that
flipped
represents
out.
the final position of it. I guess we can just use the Euler angles again. I just wanted to avoid that if I could, but I guess that's not happening. Why is this not auto-completing for me now? It hates me sometimes. Rotate, no. Euler angles equals new vector 3, initial orientation dot Euler angles dot x, y plus x angle,
Alright.
and
Initial orientation dot C, right?
yeah.
Oh yeah, Euler angles.
That will cause us problems if we
Euler
start
angle.
assigning the quaternion XYZ properties.
Oh, really?
Well, it's a very different thing than what we expect. So, oh, I don't want this. I want final orientation equals private quaternion orientation equals initial orientation, and then final orientation dot Euler angles. Actually, we can just do that, can't we? And I misspelled private. So now we're going to, as I said, I'm going to basically annex what we've got here, just in case we need it again.
You never know.
Yep. We've gone back to code that we've created before on this show a few times, and it happens in real life enough that that you should be ready for these type of things to happen. So, rotate the flipper. So what we're going to do is we're going to do transform. Actually, we're going to do transform dot rotation equals quaternion dot rotate towards initial orientation, final orientation. Okay, so now we have a max degrees delta, so we're going to change this flip time to max degrees delta.
All
so
right.
maximum degree change is what that means. So let's set this to 20, so that'll be like our 1.0f before if we were doing max angle 20. So max degrees delta. And let's see what that does first off. So we want this to only happen if we do the input thing again. Oh, that went very quickly. Oh yeah. Why do I get a feeling that that's not actually degrees at all? So let's try times mathf.deg to rad and see if that solves the problem. No, that did not solve the problem. That didn't look like that did much at all.
No. That's interesting. Very interesting.
Oh, that's... Let's try times time dot delta time. That'll probably solve it. No.
Is it moving? It is moving, just incredibly slowly.
Alright, let's look at quaternion.slurp.
Alright.
Yeah, let's do that. Let's go back to what we were doing before with the, instead of the max degrees delta, we're going to be flip time. Let's change it to slurp. Alright, so this makes more sense. We need a private float t. T equals 0. No. If input dot get button down button name.
All right.
So this is only on the frame that you first touch the button. We're going to reset the t equals 0. And then if the button is down, t plus equals time dot delta time.
Sounds good.
Flip time t divided by flip time for the final value there. Now let's see if this works. Alright, so that's doing basically what we were doing before. It automatically resets it this time, so that's actually probably good. And then then the else case is just basically the exact opposite of this. Else. Let's just do t equals 0. So get button down or get button up.
Okay.
So this will reset t in either case, and then we're going to do t plus equals time dot delta time. And we're just going to reverse these. This is going to have a visual effect that we're going to try and fix in a second here. But
sounds like a good plan.
It'll pop back to the final and initial orientations when you're hitting the buttons. So what I mean by that is get button up does not exist. Oh, input.
Oh. That's not what I expected at all.
See, the problem is if we press the buttons between times. So it's working right if you go all the way and then release, but it's not working right if you don't. So, Alright, so let's change this. Let's do initial orientation, final orientation, change this to minus equals, and let's actually cap it. So like right now, Unity's doing something automatically in the slurp thing. If t is greater than 1, it's capping it. It's t is getting much larger than 1 when we're holding the button down, but which means that we can't rely on that unless we cap it ourselves as well.
Yes.
So what we're going to do is if t is greater than flip time. T equals flip time. And then we're going to do, oh, sorry, t equals flip time. Why did I do a comparative equals there? And we're going to do the opposite here, except with 0 on this one. T is less than 0. T equals 0. And so now, we're not going to reset t.
Oh, yeah.
So let's see what this does. Goes up, goes back. Yeah, now we got it fixed. So now we can interrupt it, and it works just fine. Now let's see if this works with the negative angles. Let's see if this fixes our negative angle problem. So if we set the left flipper to -20, hit play.
It does.
Totally fixed it.
That's cool.
So that's what we're going to go with.
That's pretty neat, actually.
You know, took a long time in coming just to get something rotating. I feel like I'm out of practice in this stuff. So now let's finally do the thing where we adjust the values so this actually feels like a flipper a little bit. So flip time, let's make it to 0.1 and 0.1. Wait, what did I do before?
0.1.
0.1. Now let's make it flip up a little bit more. So let's do 35 degrees.
Negative 35 degrees.
Oh yeah, negative 35. While we're thinking about it, let's actually get rid of this because this is not true anymore, because we fixed it by changing the way that we attacked the problem in the first place. Which sometimes you just have to do that.
Mm-hmm.
So,
oh, that looks a little bit like
looks
pinball.
a little bit more like pinball. Let's see if we can flip the ball up. We're not applying a lot of force to it. That's kind of what I was worried about. Try kicking it even faster. Let's see what happens if we make it ridiculously fast.
That is ridiculously fast.
This is not going to work.
No.
So as you can see, this isn't really imparting the force that we want to impart to the ball. And part of the reason is because
those aren't technically
they're not rigid bodies.
Rigid bodies
so they're rotating, and it's really the collision system is what's happening right now is the fact that the ball is responding at all is just because the collision system is doing an interpenetration check. And it's like, oh, I'm interpenetrated, I guess I should move up and out of the situation.
Yep.
So
you saw it just jumped into the center alley there.
So yeah, exactly. So let's see what we can do. So let's change these to have rigid bodies first and see if that changes anything. So I'm just going to do, on the main one here, we're going to add a rigid body. And we're going to make sure it doesn't have used gravity. And yeah, that'll be fine for right now. So this is probably going to look exactly the same. Oh. That's funny. Yeah, that's great. That's really great. Okay, so let's go in constraints here and turn on freeze position for everything. Let's try that again.
Wait.
That was new and interesting.
I don't know why that happened.
I don't know why that happened either.
It moved upwards.
This is one of those episodes. This is going to be one of those episodes.
Did you
isn't
apply? Did you apply that? Is that just on the prefab that you did that?
Yeah,
well, I mean, you should both be.
Here, let's just double check them.
Yeah, that's. Well, kinematic. What would that do?
Maybe it has something to do with the collider being on the. That's weird.
Well, that was a little bit weird.
That's really weird.
Just a little bit weird.
Let's copy component. Paste component is new. And then delete this one. Remove component. And let's apply this to the prefab. So these look like they have the same.
Oh, look at that!
now.
You're gonna have to offset the colliders.
Oh yeah, because
it applied them at 0.
Yeah, I'll worry about that in a second. I just want to see what happens now. I don't know why that would even make a difference, honestly.
I have no idea.
It does though.
Why?
For why? Poor K.
Poor K is. It's probably due to the child-parent relationship.
Yeah.
But I mean, that's like a no-duh kind of thing, obviously, because that was the fix. We only have to offset it by, what is it, point?
Undo all this stuff that I just did if I can.
What if you just added the rigid body to the child object instead of the parent?
That's what I'm going to try now. So let's remove the rigid body from here. I don't think this is what we want, really, but let's give it a shot. Component, physics.
Does it have its
rigid
collider?
body. It does not have its collider. Good. There we go.
Whoa.
Wow.
Whoa.
I didn't freeze the position, so it's penetrating with something, I think.
Why? What is happening right there?
I think this is the reason why I get emails. How do you make a pinball game? I'm like, that should be easy, right?
You would think it would be.
Yeah.
Well, let's fix that. Let's fix that stuff real quick.
Fix it all up there.
Oh, it's using gravity still.
Oh, is it?
Yeah.
Is that the problem? Thanks.
Maybe that was the reason. Maybe that was one of the reasons.
One of the various myriad reasons.
Okay, let's see if it freaks out. Oh.
Now it's doing more of what I was expecting. So the rotation's changing, but not the...
Not the position.
Not the position.
Why don't we freeze all the rotation and position?
Because then we've gained nothing by having a rigid
true.
body at that point.
That is true.
All right.
Maybe it does really need to be on the parent object. That's so strange. Because, I mean, it was working right when it was on the parent. Wasn't it?
I don't know if it was.
It was just that the capsule collider was offset. The capsule collider. They're trying.
Okay, so here's the problem with the doing it as the child object, certainly. Since we're rotating the parent object, when the child rotates out of its initial position, this doesn't work.
Well, I'd say put it back on the parent object, the rigid body and the capsule collider, or the.
Okay, let's do that. Let's just see if that'll make it fix our problems. All right, remove component. Remove component.
Oh, it still has a capsule collider.
Oh, that probably is not helping things.
That is probably not helping things at all, actually. Maybe that was the problem.
5, 8.5. There we go. So, capsule collider, component, add physics, rigid body, no gravity, freeze position, and apply this to the prefab. Hit play.
Now we're getting that problem again, huh? But why?
I thought that worked last time.
It did. That's what's so confusing. That is really confusing.
All right. We're driving the rigid body. I'm going to actually do this back to where we were a long time ago. Add physics, capsule collider. It's good enough for me. Apply.
Oh no, it's just that the value.
Oh yeah, the value.
The value is not negative anymore. So. Well, it's starting. Just need to figure out why the rigid body was doing what it was doing. That's so weird.
All right, let's make a bumper. We're switching to bumpers. We're gonna. I want to have one thing work on this episode, so we're gonna do a bumper. Just gonna create a cylinder. We're gonna shrink it down a little bit in the y-axis, 0.25. There, that looks kind of bumperish.
A little bit, yeah.
I'm gonna put it down onto the ground. Actually, I'm gonna not put it directly on the ground. I'm gonna put it at 0.5.
Throw it on the ground.
It's actually floating slightly, but that'll be fine.
It's levitating on the ground.
Yep. And we are going to make it so we're just going to make a bumper script. C# script. Bumper. And this thing will be easy. This thing will be very easy. We should have started with this, honestly. Public float force equals, I'm going to call it 100.0 F to start, because generally with force you need pretty big numbers. Public force, float force, and yeah, I mean, like, that's really the thing, right? So void on collision enter. We're going to do what's the easiest way to do this? Apply explosion force is tempting.
It is really tempting.
Let's go with it.
All right.
So I'm going to go ahead and do a public float radius as well. And we're going to make this force radius. I'm going to make it 1.0 F. So this will be double the radius of the actual thing that we've got there, because the radius of that is probably 0.5 by default. So on collision enter, all we do is for each collider call in physics dot overlap sphere. Position is transform dot position. Position. Force radius.
Missing paren.
Yes. We're gonna do col dot rigid body dot apply. Actually, if col dot rigid body dot apply. No. Explosion, add explosion force. Force transform dot position. Force radius.
All right, that's it.
That should be it.
Theoretically.
So we're going to apply this to our bumper.
bumper.
Create a prefab for it. And hopefully this thing will...
Do nothing?
That didn't do a whole lot to it.
Put it at 1,000. Just bump that radius. Oh, maybe make the radius a little bit bigger.
I'm going to make it 1,000 first.
Okay.
Let's see what that does. There we go.
That did it. That's a bumper.
Alright, so we have a bumper. Let's make these things so that they actually flip the right direction again, just so it looks like we did some work on this show. Alright.
Bing.
We have this really lethargic gravity. Let's actually make the gravity a little bit more intense. Project settings, physics, gravity is -6. Let's just double it. Bam.
King.
And let's make that way higher. That's just not high enough. Let's another factor of 10. Why not?
Man, that's gonna just shoot off into the distance.
You think so? Bam, you're right. Called it on that one.
All right.
5,000.
I think launching the ball into the stratosphere is pretty amazing, though. Wow. Just to let you know, 5,000 apparently is a lot of explosive force.
Let's duplicate this bumper. Whoops. Duplicate. 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 Let's just see if we can make some fun stuff happen.
Let's see what happens.
Alright, well, we have bumpers that kind of work. And we have the flippers, which do work. No, they don't work at all, actually. They just work terribly.
No, they work. It's just that
they move. They don't apply any force to the balls, so we're going to have to resolve that next time. I feel like we didn't get a whole lot done in this episode, but it's a start.
Yeah, I think it'll go better next time.
Yeah, I think it will too. Anyway, thank you for joining us tonight. If you have any questions, comments, or concerns, please email me at pushypixels@pushypixels.com. You can also reach me on Twitter as @DracFire.
You can reach me if you want to. Send me an email, some words, some text, picture maybe, at philip@protosoftworks.com. You can follow me on Twitter. It's @magmalemur. I occasionally tweet. And you should buy Proton Pulse. Buy it.
Yes, and you should buy automation. Also, Phil's birthday is tomorrow, and that means
that you all get rewarded with presents of my game. It's kind of backwards, but that's okay. I've actually extended the free time period for a week now, so a week from tomorrow you should be able to get my game for free on iOS devices.
So his game is free for a whole week as opposed to just one day, and so pick it up and tell your friends, and hopefully the word of mouth will carry this at some point.
Yes, play it.
Also, one more thing, something kind of new is over here on the... Am I pointing in the right direction? I think I am. Yes. Over here on the
sidebar
thingy. It might be this direction. I think it's this one, though.
I'm pretty sure it's that one.
There is donation links for Cooking with Unity. If you want to support the show directly, you can just click any one of those and PayPal the show some moolah. No obligation, obviously. But if you like the show, click the 25-cent thing. Maybe give us a quarter or something. So anyway, thank you very much, and you guys have a great week. And next episode, I swear, we'll get the flippers working.
Download my game for free.
Yes, download his game for free. See you next week. We'll give you one more warning next week, although it'll probably be too late at that point.
It will be.
Yeah.
Well, I mean...
So we won't.
Yeah.
But, yeah, anyway. Good night.
Download it.